All right. Good morning, everybody. We've got some really interesting stuff for today. But before I begin, let me please reassure you that despite the nature of current events, okay, I checked this morning. 2 plus 2 is still 4. Triangles still have 3 sides, okay? The universe is not falling apart, okay? So there's really no need to panic. And even better news, God is still good. Right? So let that be a reassurance to you so that we can move forward with things. Now, with that, let us take a look at our current mathematical situation. We just got done dividing polynomials, right? Now, the question you may have been asking yourself, why the heck would I ever want to do that in the first place? Other than, the question says, divide this polynomial by that polynomial. What purpose does that skill serve? How does that build into the bigger picture? You're going to want to solve polynomials, right? You're going to want to figure out what values of x. Come on, let me write. There we go. Is equal to 0, right? So x equals what? That's the nature of algebra and calculus for quite a lot. You're going to find when does this function equal 0. And a lot of those functions are going to be polynomials. And we already know that probably the best solution would be to factor that guy, right? If you can get it into the form of, hey, a bunch of factors, these things in parentheses all multiplied together equals 0. We can use good old ZPP, no matter how many factors there are. And now all of a sudden, this gigantic x to the 7th plus 15x to the 6th giant polynomial breaks down into, x minus 2 equals 0, x minus 4 equals 0, x plus 1 equals 0. Right? A whole bunch of teeny tiny little linear equations you can very easily solve. And you can get your list of, here are the zeros. That would be lovely if we could do that with everything. But they're not all factorable. That's the problem. So many polynomials will not easy factor. And so we had some tools to deal with, well, what if you treated it like a quadratic? And then you could factor that, right? That was pretty good. Then we had, well, if you really have to, if you can't really factor it out immediately, see how to use a factoring technique, you can still extract a linear factor via division, right? So it's still getting at, if I can divide this out well, if I get no remainder, this was a factor, right? If I divide right, has no remainder, then this was a factor, and thus b is a 0, right? So we can actually use that. Think about what that means. There's no remainder when I divide it, because I've successfully divided a proper factor. And a proper factor represents a value of x that is a 0 of the function. A 0 of the function means if I plug x into the function, I get 0. F of b equals 0. That's what this theorem for today is telling us. That the remainder and the factors have a very intimate relationship with one another. And you can use that to test things using whatever method is easier. If a synthetic division is real quick and easy for you, go for it. Test it. Hey, boom, it worked. I got 0 remainder. This is a factor. Or just plug the number in. Substitute into the function. F of number, hey, the answer was 0. Obviously, that makes it a 0 of the function by definition, and thus x minus that is one of the factors. Now you know the division is going to go well. All right, let's take a look at what this sheet has to say. Generally, when a polynomial is divided by a linear expression, there is a remainder. Most of the time, if you randomly pick any polynomial and randomly divide by any number, you're going to get a remainder, right? There's only 3 out of infinity that aren't, right? So you get some remainder there. And what's really cool is this doesn't apply to just 0. Stay with us. Any polynomial can be written thus: the polynomial equals the divisor times the quotient plus the remainder. Right? And that's what we wrote it as our answer sometimes. You would write it as, here's my answer plus remainder divided by as a little extra fraction tacked on. Right, so we're just writing that backwards. So that means the divisor is x minus a. And the polynomial f of x would be defined as x minus a times whatever quotient plus the remainder. If I set x equal to a, look what happens. A minus a, because it's a 0, it's a factor, right? Boom, times quotient, vanish, just the remainder. So even if this wasn't a proper 0, the same rule applies, and f of a equals the remainder. Just like f of a is if it's a proper 0, it would give me 0. So you can use these interchangeably no matter what. An easy way of finding the remainder if it's divided by x minus a. You can either do the division and get your remainder, and then use that remainder to say, hey, this is what would happen if I plugged the number into the function. Or you can plug the number into the function and say, hey, this is the remainder if I divided them. You can use whichever one is easier. It's very sneaky. So here's an example. Here's a function, cubic function, right? 4 terms, okay, no GCF, so it's not like immediately factorable. But if you divide it by x minus 2, or x plus 2, so the value then of x would be a negative 2. So that leaves this much, but there's the remainder of plus 5. Well, what if you plug negative 2 into the function? Negative 2 plus 2, there it is in that form, and there it is in the original form. You get 5. That's the remainder. That's the same as plugging negative 2 into here. So you can find the remainder if this is divided. You can substitute, find 0, and find the remainder there. In short, what this means is we have not only another way of determining the output of a function, which is less handy. I mean, let's be honest. Just go ahead and substitute in if that's all you need is what is the value of the function at x equals this. But it also gives us, I would say, working the other way, use that substitution trick to quickly check, is this a factor of the polynomial? And that's what you're going to do in some of these exercises. You're going to start out just finding the remainders. And then on the next page, we can use the factor theorem to factorize, though possibly with some trial and error. So rather than having to divide by all the numbers, you can plug in the number and say, hey, if I divided by 2, or x minus 2, would that work? Is x minus 2 a factor? I don't know, try it. Plug in 2. Do you get 0? Yes. And then you factor that guy via, then you do the division, right? Plug it in. If you get 0, then divide that as a factor, reducing your polynomial. Right? That's the point of using that synthetic division. Take your big, long, high-powered polynomial, reduce it each time until you get to a point where it's like, oh, now it's a quadratic. Okay, I can just regular factor from here. And that's one tool to help you find all of the factors. Okay? So this is using knowledge of one factor in another way to help you get to the others. I hope I've made some sense. All right. Good. So there's plenty of examples on this sheet, right? They've got example, example, example. The exercises, let me highlight them for you. They're here at the bottom of the first page. Okay? And they are at the bottom of the second page on both sides. So here on the left-hand side, we're asking, is this a factor? Yes or no? And again, you have two different ways to test that. You can divide. If your remainder is 0, it worked. Or you can just substitute. But remember, you're substituting the value of x that would cause this to be 0. So don't substitute -1. Your number is always 1. It's the value of x that would cause the factor to be 0. So you'd either synthetic divide, put a 1 in the box, or substitute 1 into the function. If you get 0, it's a factor. And then over here, we're going to fully factorize the following. All right? These are all cubics. So you're looking for possibly 3 answers. Okay? Although the answers are given for you there. So you can check your work as you go. Right? So at best you get 3. 3 and 4, you don't get 3 separate ones. Because you've got a non-factorable quadratic as a result. That's okay. It said factorize, not solve for the zeros. That would be the next step. Now, spoiler alert, there's one other tool that would complete this process. Because I know what you're thinking. Well, how do I know what to test in the first place, especially when you get to here? What do I try? Where do I start? Okay? Start with some good, easy numbers. Right? Try 1, try 2. Right? Simple stuff like that. What we need next will be a way to generate a much better list than all of the numbers possible. I mean, it doesn't seem exactly reasonable, but it's at least conceivable that we could have a 0 at negative 15,000 or something. You don't know. I mean, that seems kind of high just from these small numbers. And knowing, well, it's like a textbook problem. They usually don't go that high. You don't know. Mathematically, we have no reason to eliminate negative 15,000 as a possible root. But we will have a tool, either Friday or next week, that will let us generate a much shorter list of things to try. And then this technique becomes super useful, because now we can take that short list, test all of them, and figure out which ones work. Wouldn't that be awesome? Okay, so there you have the big picture all together. I'm going to leave you with the rest of the class period to finish these exercises. 5, 10, it's what, 15 total? Yeah. Not so bad. And you've got, I think, over 15 minutes left to work. Yeah. Gosh, almost 30. That's 2 minutes apiece. You could probably finish today. Have at it. Let me know if you have any questions.